Today let us see the problem to find the eigenvalues and eigenvectors of the matrix. So first let us take the given matrix to be A. So let A is equal to the given matrix. So 6 minus 6, 5, 14 minus 13, 10, 7 minus 6, 4. So to find the, first of all, we have to find the characteristic equation. So since this is a 3 by 3 matrix, the characteristic equation is lambda cube minus S1 lambda square plus S2 lambda minus S3 is equal to 0. So here S1 is equal to the sum of the main diagonal elements. So 6 minus 13 plus 4. So it is equal to minus 3. And S2 is equal to sum of the minus of the main diagonal elements. So for 6, the minor matrix is minus 13, 10, minus 6, 4. And for the next diagonal element, minus 13, leaving the second row and second column, take the remaining elements, you will be getting 6, 5, 7, 4. Then plus third diagonal elements is 4. So it lies in third row, third column. So leave that and take the remaining elements, 6 minus 6, 14 minus 13. On cross multiplication, each determinant, therefore you will be getting minus 52, then plus 60, and then plus 24 minus 35, then plus minus 78 plus 84. So therefore the value is equal to 3. Now S3 is equal to determinant A. So we have to find the determinant value of the given matrix. So 6 into minus 52 plus 60, then plus 6 into 56 minus 70, then plus 5 into minus 84 plus 91. So on simplifying this, it is equal to 48 minus 84 plus 35, and therefore we'll be getting 83 minus 84, so it is equal to minus 1. So therefore the characteristic equation is lambda cube minus S1 lambda square. Since S1 is equal to minus 3, you will be getting 3 lambda square. Then plus S2 lambda. S2 is equal to 3. So 3 lambda, then minus S3. S3 is equal to minus 1. Therefore plus 1 is equal to 0. So this is the characteristic equation. Now we have to solve the characteristic equation. So solving the characteristic equation by using the synthetic division. So solve the characteristic equation. Lambda cube plus 3 lambda square plus 3 lambda plus 1 is equal to 0. So by synthetic division, so let us take the coefficient of lambda cube and coefficient of lambda square, coefficient of lambda, and then constant term. So by trial, we'll take the smallest number. Suppose if you are taking 1, then take 0, then add this 1 plus 0, 1, and then 1 into 1. So you'll be getting 3 plus 1, 4. And therefore 4 into 1 is a 4. And therefore you won't be getting 0. So therefore let us try for minus 1. So 1 plus 0, 1. So 1 into minus 1 is minus 1. Now 3 minus 1 will gives you 2. Then 2 into minus 1 is minus 2. So 3 minus 2 will be equal to 1. And then 1 into minus 1 is minus 1. So hence you are getting the remainder to be 0. So therefore one of the root lambda is equal to minus 1 is the root. And the other roots are given by, so the other roots we have to find out by solving this quadratic equation. So 1 into lambda square plus 2 lambda plus 1 is equal to 0. So since the equation is lambda square plus 2 lambda plus 1 is equal to 0, which can be written as lambda plus 1 the whole square is equal to 0. And therefore we'll be getting the equal roots. The equal roots are nothing but minus 1 comma minus 1. It is repeated twice. And therefore the eigenvalues are, hence the eigenvalues are lambda is equal to minus 1 comma minus 1 comma minus 1. So next we have to find the eigenvectors. Since here all the three eigenvalues are same, we have to find out three different eigenvectors by solving this equation. A minus lambda I on x is equal to 0. So A minus lambda I on x, A is a given matrix. So write down the given matrix, 6, then minus 6, 5, then 14, minus 13, then 10, then 7, minus 6, 4, then minus lambda into, it is a 3 by 3 matrix. So you have to take the 3 by 3 identity matrix, 0, 0, 1. Then it is x1, x2, x3 is equal to 0, 0. Okay. So therefore you will be getting 6 minus lambda minus 6 and then 5, 14 minus 13 minus lambda, then 10 and then 7 minus 6, 4 minus lambda. So multiplied with the eigenvectors x1, x2, x3, and this is equal to 0. So we have three cases. So since all the eigenvalues are same, so we can take when lambda is equal to minus 1. So when lambda is equal to minus 1, we'll be getting, substitute lambda is equal to minus 1 here. So 6 minus of minus 1 will become 7, minus 6, 5, 14 minus 13, then minus of minus will become plus 1. So minus 12 and then 10, 7 minus 6, 4 minus of minus a plus 1. So 4 plus 1 is a 5. x1, x2, x3 equal to 0. So on multiplication, you will be getting 7x1 minus 6x2 plus 5x3 is equal to 0 as the first equation. Second equation, 14x1 minus 12x2 plus 10x3 is equal to 0. Second equation. Third equation, 7x1 minus 6x2 plus 5x3 is equal to 0. This is third equation. Now here you can see all the three equations are one and the same here. Here 1, 2 and 3 are same equations. All the same equations. You can write it as a single equation, 7x1 minus 6x2 plus 5x3 is equal to 0. So we have to find out the three eigenvectors, but we are having only a single equation, only one equation. So first of all, let us find out the first eigenvector. So in order to find out the eigenvector, first eigenvector, let us take x1 is equal to 0. Now put x1 is equal to 0 in the first equation, in equation 1. So we get minus 6x2 plus 5x3 is equal to 0. So this implies minus 6x2 is equal to minus 5x3. Now minus sign you can cancel it, and now you divide the x2 by 5 and x3 by 6. So therefore the first eigenvector will be x1, x2, x3. x1 is equal to 0, x2 is equal to 5 and x3 is equal to 6. So this is the first eigenvector. Okay, this is the corresponding eigenvector. Now in order to find out the second eigenvector, put x2 is equal to 0 in equation 1. So substituting x2 is equal to 0, you will be getting 7x1 plus 5x3 is equal to 0. So this implies 7x1 is equal to minus 5x3. And therefore x1 by minus 5 is equal to x3 by 7. Therefore the corresponding eigenvector x2 is equal to x1 is minus 5, x2 is 0, x3 is 7. This is the second eigenvector. Now to find out the third eigenvector, put x3 is equal to 0 in equation 1. So substituting x3 is equal to 0, you will be getting 7x1 minus 6, x2 is equal to 0. So 7x1 is equal to 6x2, and this implies x1 by 6 is equal to x2 by 7. Therefore, the corresponding eigenvector x3 is equal to x1 is 6, x2 is 7, x3 is equal to 0. So this is the corresponding eigenvector. So since you can see the matrix is non-symmetric, the corresponding eigenvectors x1, x2, x3, it must be linearly independent for diagonalization. So hence, eigenvalues of the given matrix are minus 1. All the three eigenvalues are same. So minus 1, minus 1, minus 1. And eigenvectors corresponding to eigenvalue minus 1 are x1 is equal to 0, 5, 6, x2 equal to minus 5, 0, 7, x3 is equal to 6, 7, 0. Okay, I think you all can understand how to find whenever we have the three eigenvalues to be same. Thank you.